Yeah, good morning, everybody. Yeah, somebody asked about where does the nonlinearity come from? Yeah, nonlinearity is everywhere because most device itself, MOSFET itself is nonlinear in large signal input. With a large signal input, it is nonlinear, right? Say, for example, something like that. See. If you plot I1 minus I2 with respect to VI1 minus VI2, yeah, then oops, that curve looks like that. Say it is 0. This is ISS, right? ISS minus ISS. Yeah, in strong inversion, this is a square root 2 VD set, right? VGS minus VTH at this point. This is for strong inversion. With the sub-threshold weak inversion, this value is around 3 VT. Okay? Because MOSFET itself is nonlinear. Yeah, MOSFET equation, it is nonlinear with respect to gate source voltage, right? Because of a quadratic equation. Yeah, it's nonlinear. Yeah, this is a strong inversion. In the sub-threshold, the ID equals something like mu Cox W of L gamma VT square 2 square root 2 pi f minus VBS or whatever exponential VGS minus VTH, right? Yeah, it is a nonlinear function of gate source voltage, right? With a large signal input, MOSFET itself is nonlinear. So for the very small signal input, we can approximate it. It is linear. In a previous case, something like in this region, we can approximate it is linear. Approximately, it is linear. Oh yeah, let's move on with the CMFB circuit. Fully differential op-amp. We are talking about the fully differential op-amp. Yeah, this is, we have two inputs, I positive and I plus and I minus. And then we have two outputs, out plus and out minus. Yeah, because some of those sourcing current, we have 3 sourcing current, right? And we have 3 sinking current source. Some of those 2 current sources must match to maintain this output voltage in the middle. Yeah, because it's very difficult to match it. We need an active CMFB circuit. So in our case, see, we divide this one into 2, and then this half. For this half of this transistor, we applied a common mode feedback voltage, right? CMFB voltage. Yeah, this CMFB voltage is ideally this is common mode output voltage minus reference voltage plus some desired voltage, right? Something like that. Is it S? Sorry. Strong. We are using strong inversion current source. Yeah, that's the desired CMFB voltage. Yeah, we could generate this one by using ideal current source. Or this is a CMFB circuit. Say we have out P and out M, and then we use the huge resistor, 30 mega ohm there, to generate this HEP. I mean common mode output voltage. Okay, this node voltage is a common mode output voltage. It's compared with this reference voltage, common mode reference, and then generate this CMFB voltage. So this CMFB voltage will be some GM of this one, GM1 times RO. Yeah, this RO thing is what? Yeah, just RO of this one and RO of that one in parallel. Okay, that's my RO. Now let's see whether this is good or not. Yeah, see, this is a common mode output. So there is a small signal current flows like that, right? The amount of a small signal current will be this HEP GM1. Is this HEP? Yeah. Times common mode output voltage minus 1.65, right? Because see, I have one of GM1 here and another one of GM1 there. So I have two of GM1 resistor between this gate node and that gate node, right? That's why I have just one HEP here. Huh? The small signal current flows through here. This current mirror generates the exact same current here, which is 1/2 GM1 something. And then this current mirror will generate the same current here, half GM1 something. And this current mirror will generate the exact same 1/2 something like that, right? So see, if I have RO there are twice current flows through RO. It will generate this one, GM1 RO times 1/2 common mode output voltage minus reference voltage, right? Something like that. So gain should be positive, right? So it flows into RO. Gain is a positive. Then this one will make a negative feedback for the common mode circuit. So here, see, if I apply that CMFB output here from gate to drain, it is a negative gain. Source to drain, the positive gain. So it is a negative feedback circuit. Okay. Because it is a two-stage amplifier, this one makes another stage. From here to here, I have one gain stage. In the previous case, I have a burst gain stage. So usually we need a CMFB circuit. Oops, sorry. Between our node and then here. So we use the 0.1 pop. For frequency compensation. Okay? Question? Question.
디자인을 지금 NGS는 어디서 나와요? GMRO 통해서 맞추는
So your question is about what? MG1S? Where is NG1S?
원래는 VCMFB가 GMR.
Oh, okay. What you mean is, say there is no term plus V NG1S, right? Something like that, right? NG1S. So actually, we don't see it here, but this one will automatically generate by the negative feedback circuit. I just put this node voltage to that gate node. So there is some DC offset, which is VNG1S. So it will be automatically fit. Okay. Okay, so yeah, this is that real circuit. But one problem this circuit is this huge resistor. This takes a very large area. Maybe I can say something like 300 micron by 300 micron, or maybe larger than that. It is very large area, right? So if I reduce this one into 1 mega ohm, we can draw 1 mega ohm resistor in very small area. However, then I have some problem with this voltage gain, because this output resistance is pretty large. You know, this output resistance looking here, R1. Because of cascade structure, this R1 is GM RO times this thing, and RO parallel, this RO parallel that RO. This RO, that RO in parallel combination times the GM RO of this transistor. You know, and parallel with this one, there is a similar RO there, right? We have a large RO, say, our GM is very small. This GM is very small, something like this GM is around, I can say, around 130K or something like that, right? Almost. So we increased this RO into very large value, and then our GM RO is around 1,000, right? So you can see how large is my RO. Yeah, if it's 1,000, what is that? You know, my RO should be 130 mega ohm, right? Is it 130 mega ohm? Oh, how come this is too large? GM RO. So let's just see. Yeah, maybe around that. So if I put 1 mega resistor for the CMFB here, 1 meg, then see my gain will be reduced to something like 1, or maybe smaller than 1, right? Or maybe around 3 or something like that. So I cannot use a small resistor for that CMFB circuit. Yeah, one thing to note is that with a small signal, I mean with a weak inversion circuit, sometimes have some DC convergence problem. So that's why I added this huge resistor between CMFB node and the ground to improve DC convergence. Another technique is, see, we are already using it. See, there is something like dot option. Dot option G min equal 1e minus 9. This G min is a conductance used to help DC convergence of this diode circuit. Say there is a conductance G min always added across diode. The default value of this G min is just 10 to the minus 12 Siemens. Okay. So I increased into this one 10 to the minus 9. In the MOSFET circuits, we see PN junction in every source drain, right? For example, this is NMOS. Between this is source and drain. Yeah, we have a PN junction there, right? Source and bulk, drain and bulk. So G min is added across every source bulk junction and drain bulk junction. So this G min helps a lot DC convergence. If you come across a convergence problem for DC analysis, transient works fine. Some DC, sometimes dot OP may not work. with a subthreshold current. Okay. Okay, let's